As game developers, performance optimization is a demon that we have been wrestling with since the very beginning, making games for arcade machines and home consoles, and it still plagues us to this day. In the last year or two alone, there have been a number of very high-profile AAA games that have launched with pretty lackluster performance on day one, to the extent that the companies have had to issue official apologies about the state of the game. They've had to scramble to get patches out to try and fix the problems. And in some extreme cases, the launches have actually gone so poorly that the companies have ended up having to close down. So as game developers, performance optimization remains a key focus area for us. But an interesting thing that you might not have thought about before is that the majority of our focus in terms of optimization has historically been on rendering. And there are good reasons for that. It has traditionally occupied the biggest piece of our performance budget. It is how we make the pretty pictures that we use to sell and market our games. Yes, this is an actual PC game screenshot. And of course, if you buy a GPU these days when you're building a computer, it's this gigantic piece of hardware that costs more than the rest of the computer put together. So it makes sense that we focus on rendering as our main target for optimization. But all you have to do is some cursory searching online and you will find Starfield, CPU limited. Cyberpunk 2077, CPU limited. Gotham Knights, Jedi Survivor, that third act of Baldur's Gate 3, surprise, surprise, it's our old friend, the central processing unit struggling to keep up. And when I say CPU limited, generally what I'm referring to is that we're not hitting our performance targets like 60 frames a second. Our GPU utilization is low, and often you'll see just like one CPU core pegged at 100%, and that's generally a signal that the game's like heavily CPU limited. And the interesting thing to think about here is that if we compare the hardware of the CPU and the GPU manufacturers like NVIDIA and AMD are still making amazing performance gains every generation, right? Every new card is significantly faster than the old ones. On the CPU, that is not true at all. Single-threaded CPU performance has completely plateaued. Moore's law is just over, and as a result, if you write slow single-threaded CPU code today, you can expect it will run just as slowly on new hardware 3 to 5 years from now, compared to GPU stuff, which is going to be running much faster on new hardware if you launch 5 years from now, right? So it's really important to understand that if you write slow CPU code now, it's going to be slow forever. And this is exacerbated even by the fact that the way that we optimize for the GPU and the CPU is completely different. You might have seen this great white paper from Epic Games about reducing Fortnite's power consumption. And when you get into the meat of it, the main technique they rely on is called dynamic resolution. And the way that that works is that when you want to render to a high resolution output target, like a 4K television, for example, but you don't have the hardware grunt to be able to push 4K at 60 frames a second, instead, what you do is you render to a smaller resolution internal target, like 1080p, for example, and then you use one of the many well-researched magic upscaling techniques to take that 1080p image and upscale it to 4K for output. And honestly, it looks pretty good. The technique works pretty well. And the really funny thing is, when you think about it, by changing the resolution of that internal target, you essentially have this knob that you can just turn down that progressively JPEGifies your game more and more, trading visual fidelity for improved performance. And this is just one of a absolute kitchen sink of options that we have for modulating our rendering performance. We even ship a whole bunch of these to the end user. You open up the settings menu for graphics on any PC game and there'll be a whole bunch of configurable options in there to try and get the best balance of visual fidelity and performance. We have nothing like this for the CPU. There's no knob that you can just turn down that progressively turns your game into Goat Simulator, jankifying the physics and breaking the game just enough that it performs well but doesn't completely break. It's basically every game developer's worst nightmare that you end up at the end of a project and you see a frame debugger with CPU performance problems that looks like this. Thousands of small tasks, all just kind of slow. right? Because in this case, in order to actually fix this problem, you might need to make tens or hundreds or thousands of small bug fixes, all of which could affect the central logic in your game and actually break the way that the game works, right? So this all have to be regression tested and that kind of thing. So it's really important that we get ourselves into a good CPU performance situation early before we arrive at the end of the project and see something like this. And the interesting thing is when I talk to people about this, often the kind of response that I'll get from people is like, oh, well, but my computer's fast enough. My game doesn't have high requirements. It already runs fine, right? And one of the important things to think about in this case is that a very significant proportion of all of the games running on Earth right now are running off a device that uses a battery, right? And battery life is not free. These devices can't just suck 600 watts out of the wall. There's a very, very big difference between two games both hitting 60 FPS on a phone or a Nintendo Switch or something like that, one of which is running super hot and draining the battery like crazy, and the other one's running nice and cool for long periods of time. Now, I know that I'm making this seem kind of dire and scary, but the good news is that when it comes to CPU performance, if you have a good foundational intuition for what makes the computer go fast and what makes it go slow, you can get 80% of the way towards a really well-performing game with not all that much effort, as long as you start from the beginning like this. And so whenever I'm trying to develop a fundamental intuition for anything in engineering, I start with the foundational engineering question, which is, what's the problem that we're actually trying to solve as game developers writing code for games? And my assertion is that games are a real-time system, and as a result, the problems that we're trying to solve are the problems that are shared amongst all real-time systems, right? So real-time systems are very simple. All they do is they take some input and they deliver an output within a deadline, within some amount of time. So in this case for games, we're taking the buttons that the user's pressing, the current state of the game, the amount of time that's passed since the last frame, and we're delivering an image to be displayed on the screen within a deadline of about 16 milliseconds if we want to hit 60 frames a second, right? It's reasonably simple. And so what I'm going to do is I'm going to make an analogy to a different real-time system, and we're going to use that to try and understand some things more deeply about the way that the computer works. And the other real-time system that I'm choosing is a kitchen in a restaurant. So if you've played a lot of Overcooked, now is your time to shine. And so we're going to do a series of exercises where I'm basically going to say, well, the existence of X in the restaurant kind of implies the existence of Y in the computer. I know it sounds really strange, but I promise you the analogy holds. So let's get started. So when I think about work getting done in a restaurant, the first thing I think of is a chef, right? Chefs can perform a series of tasks one after another. If you have multiple chefs, they can do multiple streams of work in parallel. The existence of the chef in the restaurant implies the existence of the CPU core in the computer. You can see where I'm going with this. But of course, if you just chuck a bunch of chefs in an empty room, they're not going to be able to produce any food, right? The first thing that they need is tools, knives, chopping boards, frying pans, that kind of thing. On the computer, the tools that the CPU core uses are called instructions. But of course, chefs can't produce food with just only tools. We have one key missing piece of the puzzle, and that is ingredients. Chefs use tools on ingredients to produce their output in the same way that the CPU core uses instructions on data to produce its output. So you're kind of getting a feel for how this analogy works. So now we'll start to probe with some performance-oriented questions. You know, if we were looking at the performance in our restaurant and we were thinking, okay, well, we have to chop like 1,000 onions over a shift. Well, how fast can a chef chop one onion? Right? It's a reasonable question to ask. There are obviously very fast and efficient ways of chopping onions, just as there are very slow and stupid ways of chopping onions, right? And the equivalent question that we can ask of the computer is, what is the big O notation of this algorithm, of this piece of code? How fast will it run? But the really interesting thing is that we have jumped quite a few steps along the line and skipped over some fundamental assumptions when we're asking how fast can a chef chop an onion, right? Because before a chef can even start chopping an onion, we have to think about stuff like, well, where's the chopping board, right? Where are the onions? Where are the knife? Where are the knives? Yes, where is the knife even? What we're essentially asking in this case is, these things, the tools and ingredients, where are they stored? Where are they coming from? How do they get moved around? And this is a really important thing to understand. Big O notation only captures the speed of actually doing the work, right? But getting the tools and ingredients into the right place for the work to happen, right, is actually very important and can be extremely expensive, even occupy the lion's share of the amount of time that you're spending in some cases. If you've ever cooked like a really complicated recipe that you've never made at home, you'll know that immediately all your bench space just fills up with random ingredients. You run out of space. You're constantly moving things around and losing track of it. Moving tools and materials out of storage into the workspace and back and forth is very expensive. And so before we think about the speed of doing the work, we're going to look at storage space. How do things get stored and how do they get moved around? So in a restaurant, in terms of a chef, there's really only one place that a chef can actually do work, right? And that's right in front of them, right? If they want to do something with an onion, it's got to be on the chopping board in front of them for them to chop it in the frying pan, right? Right in front of them. And on the computer, that is called a register. Registers are the only place on a computer where work can actually happen. If you want to add two numbers together, you have to load them from somewhere else and put them into registers, and then you can add them. So it's the only place where we can actually do work. Now, if you're in a restaurant and the onion you want to chop is not right on the chopping board in front of you, where's the next closest place it could be? Well, it could kind of be in a box, say, right next to the chopping board on the bench, right? In some area within your immediate reach. You still have to reach over and grab the onion out of the box and put it on the chopping board. It's not free, but it's pretty fast, right? And on the computer, that's called the L1 cache. You can't do work in the L1 cache. You still need to move data out of L1 into a register in order to work on it. But it's pretty small and nearby, so we're happy if the data that we're looking for is in the L1 cache. Next up, if the onion that you're looking for is not in your immediate vicinity, well, kitchens usually have some storage. They have shelves, they have cupboards, that kind of thing. You might have to walk over, take the box of onions off the shelf, walk back over to the bench, put it down, open the box, take the onion out, put it on the chopping board. It's a little bit slower, a little bit further away. And on the computer, that's called the L2 cache, right? It takes a little bit longer to move something from L2 into a register than it does from L1. And now some restaurant kitchens are big enough that they have like a storage area out the back, right? Significantly further away. And this is the equivalent of the L3 on computers, right? Some computers have L3, some don't. The main thing is it's just larger storage that's further away. You probably have to tell your coworkers, hey, I'm going out the back to get something. You take whatever you're cooking off the heat so it doesn't burn. That type of thing. Significantly less convenient than grabbing it just out of a box right next to the chopping board. Now, if a customer orders, say, the salmon for your restaurant and you realize that you don't have any salmon anywhere, not on the bench, not on the shelves, not in the storage out the back, right? You're probably thinking at this point, whoa, I hope the supermarket is still open, right? You're driving out somewhere to get those ingredients. And on the computer, that is the equivalent of going out to main memory. And just to complete the metaphor, where does the supermarket get its food from? Well, it gets it delivered async from the farm, right? You don't go to the supermarket and then ask them for something that's going to come synchronously from the farm. It gets delivered async in the background, and that is the equivalent of loading something from the disk. It really is far enough away that you're basically getting the data from the farm. And an interesting thing to notice here is this general trend of, as we've gone down the list, the storage just gets larger and further away. And so a reasonable next question to ask is, well, how much larger? How much further away? So we're going to look at each type of storage, how big it is, and the latency, as in how long it takes to take data from that type of storage and bring it into a register to be worked on. And I'm going to give that number in CPU cycles. You can think of a CPU cycle as just like the base unit of operation that a CPU can do. Say adding two numbers together is like one cycle. It's not quite like that, but it's easy enough for the illustrative purposes of this example. So first up, we have the registers. They are very, very small. 8 bytes usually for the general purpose registers on a 64-bit chip. There are larger registers for doing vector operations and that kind of thing, but you don't really need to worry about them here. Obviously, the latency is 0 cycles because the value is already in the register. We don't need to move it anywhere. Next up, we have the L1 cache. A little bit larger, a little bit further away. We're up to 64 kilobytes of size now, which is still not much. You know, a 64 kilobyte image is not great quality. And now it's costing us about 3 cycles to move the value from L1 into a register. So it's not free, but it's pretty cheap. We move up to L2, again, larger, now 2 megabytes, significantly slower, 20 cycles now to get some data from L2 and move it into a register to be worked on. If we go up to L3, again, significantly larger, significantly further away. We're looking at 32 megabytes of storage in L3, and now it's costing us about 100 cycles to get data from there and move it into a register. And just like with the ingredient that I mentioned before, if we can't find our data in any levels of the cache, we call that a cache miss, and that means that we're going all the way out to main memory to try and get our data. So, as I mentioned, going out to main memory is like driving to the supermarket, and I was not kidding, right? Going out to DRAM to main memory to get data is going to run you about 200 to 300 cycles, right? 2 orders of magnitude more than L1. It really is very, very slow. And again, just to complete the metaphor, if you want to make a random read going out to disk to a modern SSD, it's going to run you about 300,000 cycles. So very, very slow, not synchronous at all. You can't really depend on that data coming back this frame. And so that brings me to a couple of kind of foundational ideas about how to optimize for real-time systems in general. You can see that because there's this escalating cost of accessing storage that gets further away, we can draw some pretty reasonable assumptions from that, right? The first one is that if you're going to do something, you should do it as many times as you can. If you're going to pay to set up to do a task, you should amortize that cost over doing the task in bulk as many times as you can. And a very similar idea is that if you're going to bother to move from one place to another, you may as well take as many things with you as you can, right? Don't just move one thing, move a whole bunch of things. And this image in the bottom right corner here will give you a little clue for where I'm going with this next, right? Because if you want to get something from the supermarket and bring it back to your restaurant, you have to take some kind of vehicle, right? You're driving a truck or you're driving a van out there. And the interesting thing here is trucks and vans have a limited capacity, right? You can't just go and buy the entire supermarket and drive it back to the restaurant in one trip. In exactly the same way, the thing that goes out to main memory and gets data for you and comes back is called the cache line, and it has a capacity of a whopping 64 bytes. That's bytes with a B, right? It is very, very small. Just to reiterate, you're paying 200 to 300 cycles for 64 bytes of data. It is extravagantly expensive, and just to really hammer home the point, probably the most famous performance optimization of all time in game development is John Carmack's fast inverse square root from Quake 3. And the way that this works is they needed to calculate the reciprocal of a square root of a floating point number, and square roots of floating points were quite expensive, right? And they had to do this thousands or tens of thousands of times a frame, so it really added up, and so they developed an approximation that was much faster than having to actually run the square root calculation instruction. It involves some absolutely unholy floating point bit manipulation. You want to know how much time this actually saves? How expensive a floating point square root was on a Pentium 3 in 1999? About 30 cycles. The most famous game dev performance optimization of all time was to save 30 cycles, and you're paying 200 to 300 just for 64 bytes of data back from main memory. I cannot overstate the impact of the interaction with the cache and with memory that it has on the performance of your code. And it's not captured by things like big O notation at all, right? It's really important to understand this. And so, given that cache lines are so expensive and so small, it's very reasonable to ask, like, well, what's in the cache line, right? We should try and get the best value for what we're paying, if it is so expensive. And the way that the cache line works is that when you access a variable in code, say we're accessing an integer on some object, we generate a load instruction. The cache line goes out to main memory, to the address that we asked for, gets us our integer, and will load 64 bytes in a straight line from the address that we asked for. So in this case, we'll get our 4 bytes of integer, and then we get 60 bytes immediately following that integer in memory. And so that begs the question, when was the last time that you accessed a random variable in your code and you actually actively thought about what was in the subsequent 60 bytes after, right? You probably never do. And that's why this is so important to understand that interaction with the cache is such a silent killer. Because at the very least, in John Carmack's example, if you know that square roots are slow, you can at least search your code base for square roots. You can at least see where the square roots are, right? As soon as your application gets to a reasonable level of complexity, it becomes very, very hard to reason about when a variable access like this will generate, a cache miss, what is going to be immediately in the cache line following this value kind of thing. So rather than agonize about the very specific cases, what I'm going to give you is 4 general rules of thumb that you can use to write reasonably fast code for the CPU. And if you just apply the rules of thumb, you'll get most of the way there. And then you can worry about specific examples if you have very hot loops in a certain circumstance. And so the first rule is that obviously, you want your layout of your data to be as efficient as possible because we want to get the most bang for the buck that we can with that 64 bytes of the cache line. So use the smallest data types that you can to fit more things in the cache line. You want to store your data by locality of use. So things that are packed together in memory should be used within quick succession so that you can maximize the cache line and the 64 kilobytes or so of L1 that you have. The TLDR here is just don't waste the cache line. Second rule of thumb is that if you're going to bother to do something, do it as many times as you can. Do, anything in bulk while you have the tools and the instructions still available to you. A nice little trick that I tend to use here is think really hard about whether a function should ever take one of something or whether you can convert it to take an array of things instead. Third rule of thumb, do as much ahead of time as you possibly can. If you don't need to do it at real time, don't, right? In the same way that we prepare ingredients before the dinner shift starts, we pre-compute as many things before we ship our game or on startup before we enter into our frame loop, that kind of thing, as we can. Why do you think it's called baking? Lighting needs to be rebaked. It's because when you open your bakery at 7 a.m., you don't open with nothing and then have a customer come in and be like, I'd like a loaf of sourdough bread, please. And you're like, oh, cool, thanks for the money. That'll be 36 hours. You prepare that stuff before the real-time constraints start so you can actually adhere to your input-output latency requirements. And the fourth rule of thumb, which has a big asterisk on it because I'm not going to go into it in much detail, is parallelism, right? It's a whole beast of a topic, so I won't talk that much about it. But general high-level rule of thumb, if you have multiple chefs, you should be using them. Right? Your restaurant's not going to do well if you have one chef in the kitchen, sweating and cranking out meals for all the customers and the other 7 chefs are in the back lane smoking and watching TikTok. It sounds ridiculous, but that's literally what's happening when you have one CPU core pegged at 100%. And a general rule of thumb for writing multi-threaded code is that you want your cores to be doing 2 different streams of work that don't require any synchronization and then having a cheap combine operation at the end rather than having the 2 tasks try and synchronize between them. In the same way that chefs produce kind of half the ingredients for a dish each, and then they all just get quickly plated together into the one dish at the end. It's also worth mentioning, just as an aside, how well this analogy holds, right? in exactly the same way that each chef has a workspace right in front of them, each CPU core has its own L1 cache, right? So that's a really important thing to understand. When I told you you only get 64 kilobytes of L1 cache, that's per core, right? So if you're only using one core, you're essentially throwing away the majority of all of your fastest memory that you have access to. It's incredibly wasteful to only do one thing on one CPU core. And now you can start to understand why single CPU bound things are so slow. So just as an overview, again, efficient layout and storage of your data. If you're going to do one thing, if you're going to pay to set up to do something, do it as many times as you can. Do as much work ahead of time as you can. And if you really have to do it at real time, try and do multiple things at the same time. So that's a lot of abstract kind of high-level theory about the way that the computer works, and now I want to get into some explicitly practical examples. This is going to be a lot of fun. What we're going to do is we're going to look at a piece of code that is very common in games. You will have seen something very similar to this at some point, and we're going to apply progressive little tweaks to just get it working faster and faster on the CPU. So you've definitely seen code like this before. We have a class enemy, which extends from a game object, an entity, an actor, that type of thing. And then it has a bunch of properties associated with it. A boolean that says whether it's dead or alive, has a string ID, has a bool that says whether it's in frenzy mode and has increased attack speed, has a callback that gets called when the enemy dies, like a function pointer or a delegate or something like that gets called with the string ID when the enemy dies. And it has an update function, which is one of those magical game engine things that gets called automatically once per frame, a tick function. And inside that update function, there's a bunch of if statements that say, like, if the enemy's dead, call the on-death callback. Otherwise, if the enemy's in frenzy, either because of a global override or because it's locally in frenzy, we handle the frenzy mode. Otherwise, we just do the standard enemy behavior. So the very first big sweeping optimization that we're going to make here is we are going to get rid of that update function, right? We're going to split this into two things. A data class that just has those three member variables, the dead, the ID, and the frenzy. And we're going to convert that update into a bulk processing function that takes a list of enemies and processes a whole bunch of enemies at a time. There are so many reasons why this makes things a lot faster. In fact, Unity actually officially recommends that you do this. They call their pattern an update manager or something because, of course, you know, Unity loves inventing new words for things that already exist. There are so many reasons why this is so much faster to do it this way, but a picture is really worth 1,000 words. So here is a wonderful visualization from Takahashi Keijiro, who actually works at Unity. And it shows the difference between sort of random access of a bunch of different pieces of data that are all different sizes and fragmented in memory versus just like burning through a linear array of packed data of the same type. So it gives you an idea of why one of these is much faster than the other. So that's the first change that we're going to make. The next thing that we're going to do is get rid of that callback function. Get rid of that on-death delegate or function pointer. This is another optimization that is very hard to quantify because the impact on performance is functionally unlimited, right? One of the most important things that you'll understand now, because I've explained how the cache line works, right, is that when we access something like the enemy, when we define that enemy variable, we want to make sure that what we get in the cache line afterwards is packed data that we're actually going to use, right? But when we call this on-death function, we call this code we can refer to it as unmanaged because anything could happen. Right, we have completely lost control of the performance characteristics of this loop because calling this on-death function could do anything. It could make calls to the network. It could write things to the disk. It could call a whole bunch of Unity APIs. You know, it could evict the entire L1 cache. right? We've lost control of the performance characteristics of this function. So instead, what I'm going to do in this case is I'm just going to inline what was inside that function anyway, which is just removing the enemy from the list. You might not be able to do this in practice. I'll give you some techniques to manage that, but yeah, just for illustrative purposes, we're just inlining the functionality that was inside that callback. This is something sometimes referred to as the observer pattern, and in a general sense, it's just performance poison. It can get out of control very quickly. So now that we've got the two sort of large, high-level optimizations out of the way, we'll start looking at stuff that we can actually measure. So the very first thing we're going to do next is called hoisting invariance. Now, I know this sounds, like complicated technical jargon, but it's actually very simple, right? Invariant is just not varying, non-changing, right? Hoisting is just lifting up. So it just means lifting things that don't change out of loops. So in this case, because you now understand that just accessing a variable can be very expensive, if variable accesses are always going to result in the same thing coming back, right? We can expect that inside our loop, the global frenzy on the global config is always going to return the same value, right? So we can just lift it out of the loop and cache it locally so we don't have to make that load out of memory every single time. And as soon as we do this, it's just 10% faster, right? So we started from a baseline of 309 and we've come down to 284. So hoisting invariance is a great technique to learn. Next thing we're going to do is we're just going to go ahead and convert that class to a struct. And as soon as we do that, it's 30% faster, right? Just a big win immediately. All we're doing is changing the keyword. And the reason that this happens in this case is because of the way that classes and structs are stored in arrays. So structs, when we store them in arrays, are packed right next to each other because they're a value type, right? They're all stored in one long linear stripe in memory, same as integers or floats would be inside an array. Compared to classes, which instead, are actually not stored inline in an array. An array of classes is actually just an array of pointers, right? And the pointers each point to different locations on the managed heap. Now, if we're lucky, those classes might be nearby on the managed heap, but in the worst case, right, every single one of them could be stored in a very different location. And so you can understand now from what we've learned about cache lines, right, when we access a struct in that array, the only thing we're going to get back in our cache line is more structs, because the structs are all packed next to each other. If we access a class in our array, the only thing we're going to get back in our cache line is lots of pointers, right, packed into the cache line. And then we need to make additional individual requests to memory out to the heap to get the actual class that the pointer's pointing to, right? And in the very worst case, all of those accesses could be L2 cache misses, right, which are very slow. And, obviously it makes it even worse that we have a string ID on there. So it's, it's another indirect request to memory. And now you can start to see how nested class structures with lots of nested pointers tend to add up in terms of the cost of accessing them in memory. So that's the reason that changing to a struct makes it so much faster in this case. Next thing that we're going to talk about is alignment. Now, if you've heard of memory alignment before, it probably comes across as like scary and confusing, but it's actually very simple in practical terms. The way that you can think about it is a struct is like a recipe for how to create the thing that it defines, right? So in this case, it's like our recipe for our enemy, and inside our struct, we're thinking about it as like it's a set of boxes that contain all the ingredients to make this recipe that we're describing. And the quirk of the way that computers work is that all of those boxes need to be the same size, right? So to store the boxes of ingredients that make up our enemy, in order to have a box size that's big enough, we just use the size of the largest thing in the struct. So the largest thing in the struct is that string ID, it's 8 bytes. Those two booleans are both 1 byte. And so in this case, we have an 8-byte container size that we're using to lay out our enemy in memory. And because our enemy struct is like a recipe, we can follow it line by line and lay it out in memory to see how it's going to work. So We're laying them out in order. We take the first boolean for dead. It's 1 byte. It goes into the first container. Okay, fine. Then we try and fit the 8-byte string ID in, and we don't have enough space in that first container anymore. There's only 7 bytes left, right? So the 8-byte ID has to go into the second container. Then because it's like a recipe and we're laying out things in order, the frenzy bool has to go after the string ID. So that goes into the third container, right? Now we have a 24-byte struct with 14 bytes of waste, 7 bytes in that first container and 7 in the last container, right? 14 out of 24 bytes wasted is 58% waste. So even though we've managed to pack all of our data into a cache line by using structs, we're still wasting 58% of that cache line on pointless data, right? So in this case, we're going to make the tiniest little change. The only thing that we're going to do is we're going to swap the declaration order of that string ID and the dead boolean. And because you know how alignment works now, you can tell obviously what's going to happen. The 8-byte string ID can go fit into the first container now, and the dead and frenzy booleans can just fit one after another into the second container. So our struct size has come down from 24 to 16, and now we only have 6 bytes of waste, and the only thing that we had to do was change the order of the variables declared inside the struct, which is pretty crazy when you think about it, but when you understand how it actually works on the hardware, it makes perfect sense, right? So as soon as we do that, because the structs are all smaller, we're now 10% faster down to 190. This can be even more of a difference depending on the situation, how the prefetch is working, that kind of thing. But in a general sense, again, just smaller, more tightly packed data with less waste is what we want to be going for. I know you're probably galaxy braining on like thinking about the alignment of all of your structs now, but don't think too hard. It's very easy to do it. All you have to do is order it from the largest to the smallest, and you're guaranteed to have the most packed outcome. So in this case, we put the 8-byte one first and then the 2 1-byte ones after. So the next thing we're going to do is we're going to look at those 2 booleans, because to me, when I see multiple booleans, I start to get suspicious, because something that we don't often think about with booleans in computer science in general is that they are combinatorial in terms of the number of states that they can encode. And what that means is if I have 1 boolean, I have 2 possible states, right? If I have 2 booleans, I have 4 possible states. 3 booleans is 8 states, etc. The number increases very rapidly, right? And often, a lot of those states actually don't make sense. So in this case, we're looking at the dead and the frenzy booleans. It's like, okay, if an enemy's alive and it's in frenzy mode, that makes perfect sense. If an enemy's alive and it's not in frenzy mode, also okay. If an enemy's dead and in frenzy mode, if it's dead and not in frenzy mode, like what does that distinction mean? Like to me, that sounds like a classic example of like a bug that comes up later when QA is like, oh yeah, when you get to the shaman boss, he resurrects goblins and sometimes they just come back to life in frenzy mode and you're like, oh yeah, the frenzy boolean, I forgot to set it to false when the enemy dies, like that type of thing. So this is a code cleanliness issue, not just a performance problem. This can also help allow you to capture better representation of all of the valid states of your program. So what we're going to do is we're going to replace those 2 booleans with an enum that just encodes all of the valid states. So instead of having a dead and a frenzy bool, we have 3 states in an enum: alive, normal, alive, frenzy, and dead. So that dead, normal, and dead frenzy state is not encoded anymore. And predictably, when we make this change, the code doesn't get any faster. And you know why? Because we looked at the alignment from before. So you know that first container is still 8 bytes of the ID. And the second container, the enum is just fitting into the second container where the 2 bools were fitting before. So the struct's the same size. As a result, the code doesn't get any faster. Here's the interesting thing though. That enum is 4 bytes, right? 4 bytes is an enormous amount of range. It gives you 4 and a bit billion values, the maximum amount of memory that you could have on a 32-bit operating system, right? It's a huge number. We only need 3 values, right? We don't need 4 billion values. So a very small change that we can do, this works in both C# and most C++ compilers, is you can just slap :byte on the end of that enemy state enum, and that just tells the compiler, hey, I want this enum to be encapsulated in 1 byte instead of 4, which is the default. There's very little downside to doing this. The compiler will actually complain if you overflow the size of the enum that you're using, so you don't have to worry about that. And, predictably, when we downsize to a byte, the code doesn't get any faster again, because we're in exactly the same situation alignment-wise. The enum state is just 1 byte now instead of 4 in that second container. So it might seem that this is pointless from a performance perspective, but you've got to remember that if you're using this enum somewhere else, like packing it into an array, you can now fit 4 times more of those enums in an array than you could before when they were 4 bytes in size. And indeed, if you benchmark this, it does make a significant difference to the speed, so it's worth thinking about that as well. The next thing that we're going to do, as you can probably predict, seeing that 8-byte container and the 1 byte state afterwards, we're going to get rid of that string. Just don't use strings. Please don't use strings. There is this classic depressing example of in Grand Theft Auto Online, someone noticed that it was taking a very long time to load into the world, and 7 or 8 minutes, something verging on intolerable. And they actually went and profiled the application and found that it was spending 70% of that loading time just with a single core pegged at 100%, struggling to process a 10 megabyte JSON string. Right? And people look at this thing and say like, oh, well, Rockstar, they're just bad developers or something. They're absolutely not, right? No way. And I can tell you that what most likely happened is when the game shipped, the config file, the JSON config file, was quite small and there was no noticeable performance impact at all, right? And then as you push out patches and that config file grows slowly, the performance just craters exponentially, because strings are just full of landmines that don't necessarily show up until the scale starts to increase a little bit more. General rule of thumb here, if a human isn't going to read it, don't use a string, use something else. And indeed, what we're going to do here is we're going to replace that string ID with an unsigned integer. Again, like I said before, a 4-byte integer will give you 4 billion values in range. So if you're planning to spawn more than 4 billion enemies in your game, come chat to me. I'm very interested in what you're doing, right? If this container's too small. But because the ID was the biggest thing and still is the biggest member in the struct, the container size that we talked about before comes down from 8 bytes to 4 bytes instead. So now we have that 4-byte ID, our 1 byte state enum is in the second container, so the struct has come down from 16 to just 8 bytes in size, and as a result we get a 20% performance increase by getting rid of that string. And now we're down to 153, which is about double the speed of our original for loop, just through this progressive little series of tweaks. And so we're going to keep going. So now what I'm going to do is I'm going to reveal some performance issues that are lurking under the surface in the same way that they were with that string that I showed you before. So I'm going to increase the number of enemies by 10 times and the number of deaths, and as a result, deletions from the list by 100 times per frame. And the performance just degrades exponentially when we do this, right? And the main reason for it is that enemies.removeAt function call. So when you use a list wrapper in something like C# or C++ even, the way that they work is they provide you 2 guarantees, right? The first one is that the elements in the list will always remain in order, and the second one is that there are no holes. And so as a result, if you delete the first element in the list, it actually has to shuffle every single subsequent element in the list backwards by 1 to fill the hole and maintain the ordering. And as a result, every deletion is incurring this, big cost on moving things around in memory in the list. So the first thing that we're going to do is just move that deletion call to a bulk delete at the end of the loop instead of in every iteration. And it's immediately just 3 times faster, right? This isn't even implemented amazingly well. You know, when we call remove all, it still has to iterate the entire array of enemies again and run a delegate on every single one of them to check if they're dead. But remove all internally at least waits until you've done all the deletions before it does that compaction operation, rather than compacting every single time after every delete, right? And that makes such a significant difference. And the interesting thing about this is we can actually go further, right? Because do we actually care about the things staying in order or there being no holes, right? Those are the important questions to ask. So in this case, it's really important to understand, like, maintaining a stable position in memory is a cost that you have to pay. And so in our case, we actually don't care about the enemies being in the same order, right? They have an ID already for us to identify them, and we just want to iterate through all of them. We don't really care about what order we're iterating through them in. So what we're going to do is we're going to replace that list with a very simple data structure called a swap back array. And the way that swap back arrays work is that if I request to delete the element at position 6, what we do, instead of shuffling positions 7 to 12 backwards by 1, instead, we're going to copy element 12 over the top of element 6, hence swap back, right? We're swapping the back element of the array into the position that we're deleting, and then we just reduce the count of the array by 1 to clip off the duplicate element 12. So now we've successfully deleted element 6, and the elements are not in the same order anymore, but we don't care, right? Because that's not part of our requirements, right? So I built a swap back array that just has a compatible interface with the generic list in C#. So all I had to do was change the keyword, and immediately it's just 4 times faster again, right? And now it's so fast that we're actually going faster than before we increase the number of enemies by 10 times. If we reduce the enemy count back down to our original counts, we're looking at a 20 times speed up from our original for loop, right? This is starting to be very significant, and you probably know by now that what I'm going to say is we're going to keep going. So the next thing that we're going to do is one of my favorite optimization techniques. It's called avoiding last-minute decision-making. And when I'm talking about last-minute decision-making, I'm talking about things like these if statements, right? So we're in our loop. We want to be processing our data in bulk, but at the last minute, we have to decide what to do every time. It's like a chef being handed a Post-it note that says, chop 1 onion. So they get out the onions, they get the stuff, they chop the onion, okay, good. They get handed another Post-it note that says, fry an egg. So it's like, okay, put away all the onion stuff. Where's the, get the egg, get the frying pan, okay, fry the egg, okay, done, great. Then they get handed another Post-it note that's like, chop an onion. And they're like, oh, God, okay, put it all away, get the onion stuff out again. This in general is very bad for processing things in bulk. And so what we're going to do instead, the opposite of last minute decision making, is making decisions ahead of time, right? So what we're going to do is, instead of having these if statements inside a loop over all of our enemies, we're just going to split our enemies into 3 different arrays. We've got an array of normal enemies, an array of frenzy enemies, an array of dead enemies. And we can now process them all separately. We can have a process normal enemies function that we hand an array of normal enemies that has no if statements in it at all, right? Because it doesn't need to check that they're dead. It doesn't need to check that they're in frenzy, because it knows, based on, the fact that that's what the function is expecting to do when it gets past an array of enemies. It's like, okay, I know that I'm expecting to get an array of enemies that all adhere to these particular requirements. Same with the frenzy, same with the dead enemies, right? And if you're really astute here, you will have noticed, right, that when I said infer, one of the interesting things about that is we actually don't need our enemy state enum at all anymore, right? Because by just passing the array of normal enemies to a function that deals with normal enemies, we have implicitly stored the fact that they are normal in the array membership, right? We've hidden the information in there. So an enemy's dead just by virtue of it being in the dead enemy's array. We don't even need to store that data. And this wonderful technique is called taking information out of band. I first heard it from Andrew Kelley, the Zig creator, in his talk. I think it's Practical DOD, Practical Data Oriented Design, wonderful talk. You should definitely check it out. But this technique is super valuable. Splitting things into arrays, you can eliminate booleans, you can eliminate enums, and just imply that information based on the array membership. And making these changes, of course, means that now we just have that single unsigned integer as our enemy. We could even just get rid of the struct if we wanted to and just have an array of integer IDs for our enemies, for example. But anyway, these changes together, again, give us another double increase in our speed, and we're now at about 40 times faster than the original for loop. So this is a pretty amazing change. And we could keep going into SIMD, parallelism, IPC, land kind of thing if we knew a bit more about the implementation of the enemies, but we're going to stop there because that's a lot for one talk, especially if you've never seen these concepts before. And I'm going to leave you with just one kind of parting thought, which is that this is quite a lot of tests when you look at this, laid out in this table. And a lot of these could probably be dismissed as a pointless micro-optimization if they were looked at in isolation, in one pull request and that kind of thing. But that's the thing. When you're looking at a contested resource like the cache, the degradation of performance is not additive, right? Each of these things does not function as an individual. It's multiplicative. They all affect each other, and the code becomes either exponentially faster or exponentially slower based on the interaction of multiple things, right? Anyone who drives a car will tell you that traffic doesn't just get linearly worse the more cars there are on the road, right? It's sort of okay until the point that it just ramps suddenly into complete gridlock, right? Because the road is a contested resource, just like the cache. So it's really important to remember that this type of approach is something that you can just be doing here and there, making small, sensible decisions about writing code that the CPU is going to be able to perform well on, and just avoiding things that are likely to explode when the scale gets particularly high. And not to mention, this type of programming is really, really fun as well. I just love doing this type of thing. That is the talk. I hope you enjoyed it. If you want to look at some other things in the same topic area, as I mentioned, of course, that Andrew Kelley talk, Practical DoD, is very good. The foundational talk in this topic, of course, is Data-Oriented Design in C++ by Mike Acton at CPPCon, I think in 2014, maybe, if I remember correctly. The iconic red Hawaiian shirt. Absolutely strongly recommend watching that. And of course, there is some fantastic modern performance-oriented educational material from Casey Muratori as well, which is highly recommended. Hope you enjoyed the talk. If you ever want to chat to me about programming or game dev or just, performance optimization in general, I'm on a bunch of social media at Nick Barker again, and I'm always happy for a chat. Thanks.